Hello everybody, in this video we're going to cover section 17.1, a review of redox chemistry. We're going to describe the defining traits of redox chemistry. We're going to identify the oxidant and reductant of a redox reaction, and we're going to learn about balancing chemical equations for redox reactions. So first, what is a redox reaction? A redox reaction is a reduction-oxidation reaction, and it entails that there's some sort of change to the oxidation number for one or more of the elements. What is the oxidation number? The oxidation number of an element in a compound is essentially an assessment of how the electronic environment of its atoms is different in comparison to atoms of the pure element. All right. By definition, the oxidation number of an atom and an element, so if we just had a free atom that was neutral, is going to be 0. For an atom and a compound where we have chemical bonding, the oxidation number is equal to the charge the atom would have in a compound if the compound were ionic. The sum of the oxidation numbers for all atoms in a molecule is equal to the charge on the molecule. So let's look at a couple of examples. If we have an ionic, then assessing the oxidation number is pretty easy. We know how to do this at this point. For instance, if we had calcium fluoride, we know calcium always has a 2+ charge. Fluorine takes on a -1 charge. Therefore, the oxidation number for fluorine is -1. And the oxidation number of the calcium is going to be +2. If we had something like a transition metal here where we weren't sure what their oxidation number is just by looking at it, we could figure it out from the context of the anion that it was bound to. When we have covalent molecules, things get a little bit trickier. So I want to think back to this first image that we had when we started this semester, where we have partial positive charges on our hydrogens and partial negative charges on our oxygen. Now, 2 partial negative charges are going towards the oxygen, one from each one of these bonds. So if these weren't partial charges, what would wind up happening is we would have a -2 charge on oxygen here, and we'd have +1 charges on each of our hydrogens here. Therefore, the oxidation number here would be hydrogen has a +1 charge, and the oxidation number of oxygen would be -2. So we kind of have to think, what if these just weren't partial charges, but instead full charges? A little bit more tricky example would be one like this, where we're looking at a nitrate anion, a polyatomic, okay? It has multiple different states that it could be in. It has this resonance structure, all right? And the first thing we want to do is assess what is the charge on this overall molecule. So if I have 1 positive charge and 2 negative charges, well, one of the negative charges and the positive charge is going to cancel each other out. So the overall molecule has a -1 charge. So I'm going to set that to be the answer down here where I'm adding up the charges. The positive plus the negative charges would be -1. If we think about the dipoles here, we would see that oxygen is more electronegative than nitrogen. So each of these is going to be pulling on that nitrogen. Okay, so this oxygen would have a formal -1 charge and a partial -1 charge due to the dipole for a total of -2. Here, where we have a double bond, well, each one of those bonds is going to pull a partial -1 charge for a total charge of -2 on that oxygen as well. And so with this guy here, all right, this would also have a -2. So all 3 of our oxygen atoms are contributing a -2 to the overall charge. That means that nitrogen here has to be a +5 in order for this math to work out and for us to get -1 altogether. If we're balancing redox reactions, we have a list of rules here. I'm not going to go through an example in this video, but I have many that I did in the homework problems. So you should look through that and see how you go about balancing these kind of reactions. It's a little trickier than other ones because we not only have to balance the atoms on either side of these reactions, but we also have to balance the number of electrons that were transferred. So you start by writing out a skeletal equation for the oxidation and reduction half reactions. Okay, we're going to see some half reactions in the next couple videos to kind of cement what that means in our minds. Then we're going to balance each of the half reactions for everything except for hydrogen and oxygen. And that it's going to include balancing, so any of the atoms that aren't hydrogen and oxygen. To balance the oxygens, we're going to add water to one side, and then we're going to balance the hydrogen by adding protons to another side. And then we have to balance each half reaction for the charge, okay, by adding electrons to either side in order to get all the charges to add up correctly. And if necessary, we're going to multiply both half reactions so that the number of electrons consumed in one is equal to the number produced in the other. So we have to balance our electrons after we've done balancing our atoms. Then we're going to add the two half reactions and simplify, as we've done a couple of times already. This would give us a reaction that was in acidic medium. Most all of these redox reactions are either going to be in some sort of acidic medium or in a basic medium. If we do want it to be in basic medium, then we're going to add hydroxide ions to the equation that we've obtained for in this step here in order to neutralize all of the free protons in the solution. And then you're going to wind up with hydroxide on one side, and then you're going to have waters on the other side in place of your protons.